Here we're going to look at how we can use initial rate data to work out the order of a reaction and therefore deduce a rate equation. In questions like these, we're looking for where one of the reactants' concentrations remain constant. And we can see in experiments 1 and 2, the concentration of B's remain constant. So the only thing which must be affecting the rate is the change in concentration of A. Concentration of A is increased by a factor of 2. And that's caused the rate to increase by a factor of 4, which is 2 squared. So it's second order with respect to A. We can see in experiments 1 and 3, the concentration of A has remained constant. So the only thing which affects the rate in experiments 1 and 3 is the change in concentration of B, which has increased by a factor of 2. There has been no change in the rate. So therefore it must be 0 order with respect to B. So my rate equation then is rate is equal to Ka squared. Let's have a look at another example. So again, I can highlight these two. The concentration of B has remained constant. The only thing affecting the rate is the change in concentration of A. Concentration of A is increased by a factor of 4, and that's caused the rate to also increase by a factor of 4. So it must be first order with respect to A. Now, we haven't been given any data where the concentration of A is constant. We can use the fact that it's first order with respect to A to work out the order with respect to B. Now, in experiments 2 and 3, the rate is increased by a factor of 4. And the change in rate is due to the product of how A has caused the rate to change and how B has caused the rate to change. So the rate has increased by a factor of 4. Now, it's first order with respect to A, and we've increased the concentration of A by a factor of 2, so that would cause the rate to increase by a factor of 2. So how B is causing the rate to change is this missing number here. And obviously that missing number there is a 2. So whatever you've done to the concentration of B has caused the rate to increase by a factor of 2. And we can see that in experiments 2 to 3, the concentration of B is increased by a factor of 2. That's caused the rate to increase by a factor of 2. So it's first order with respect to B. And my rate equation then is rate is equal to Ka B. Let's have a look at my next example. Again, I can highlight these two bits of data. The concentration of A is constant. The only thing therefore affecting the rate is the change in concentration of B. And here it's increased by a factor of 2. The rate is increased by a factor of 4, which is 2 squared. So it's second order with respect to B. Now looking at experiments 2 and 3, we can see the concentration of B is increased by a factor of 4. And the rate is increased by a factor of 8. So remember, this change in rate is due to a combination of how A has caused the rate to change and how B has caused the rate to change. So the rate has increased by a factor of 8, but we've increased the concentration of B by a factor of 4. Because it's second order, that would make the rate increase by a factor of 16. So this number here is how A has caused the rate to change, and this number is 0.5. Okay. And if we look at how the concentration of A has changed in experiments 2 to 3, again, it's gone down by a factor of 2, and that's caused the rate to go down by a factor of 2 as well. So it's first order with respect to A. So rate is equal to Ka B squared. My last example looks at an experiment where I've got 3 different reactants. We can highlight the concentrations of A and C in experiments 2 and 3 as they are constant, and therefore the only thing affecting the rate is the change in concentration of B, and that's increased there by a factor of 2, and it's caused the rate to increase by a factor of 2 as well. So it's first order with respect to B. We can now look at this being constant in experiments 1 and 2, So we can ignore that. And now we know that it's first order with respect to B, and we can use that to work out the order with respect to C. Now in experiments 1 and 2, we've got an increase in rate of 8 by a factor of 8. The rate has increased by a factor of 8. And we know that it's first order with respect to B, and we've increased the concentration of B by a factor of 4. And because it's first order with respect to B, it must have made the rate increase by a factor of 4. So whatever you've done to the concentration of C has caused the rate to increase by a factor of 2. And you can see that you've increased the concentration of C by a factor of 2, so it must be first order with C. Now look at experiments 3 and 4, where we've got a change in concentration of A. Now, it's first order with respect to B and C, and we can see that in experiments 3 and 4, the concentration of B has increased by a factor of 4, but the concentration of C has decreased by a factor of 4. And because they're both first order, the effect of this cancels the effect of this, because increasing the concentration of B by a factor of 4 would make the rate increase by a factor of 4, but decreasing the concentration of C by a factor of 4 will cause the rate to decrease by a factor of 4. So we can kind of ignore anything here now. And therefore the only thing which affects the rate must be the change in concentration of A. We can see that it's gone up there by a factor of 2, and the rate, there has been no change. So it must be 0 order with respect to A. So my rate equation then becomes rate is equal to K BC. So there you've got 4 examples of how you can use initial rate data to work out orders of reaction and therefore deduce rate equations.